You fix one bug, and two more appear. The system didn't break, it reacted. Most of us were taught to think about software in pieces. A function here, a module there, a bug on line 47. When something fails, we zoom in closer. The assumption is honest. If each piece is correct, the whole must be correct. But production doesn't work that way. The pieces talk to each other. They compete for resources. A small change in the database layer can silently erode cache assumptions made months ago. A micro-optimization in one service can create a traffic jam in another. We end up exhausted, chasing symptoms whose real causes live somewhere we never thought to look. Systems thinking is a way to step back and see the currents. It's not a framework. It's not a tool you install. It's a habit of asking a different question. Instead of, what's wrong with this component? You start asking, what changed in the relationships? This isn't academic theory. I've seen teams cut incident response time by 40% just by drawing a simple loop diagram during a postmortem. I've seen a junior developer spot a cascading failure that 4 senior engineers missed because she drew the system, not just the stack trace. What I'm going to share here worked for me. Your results may vary, but the mental shift is free, and it lasts. We'll walk through 5 ideas, what a system really is, how feedback loops create behavior, where to find leverage, why local optimization is so tempting and so dangerous, and how to start practicing on Monday morning without changing a single line of code. Take a breath. We're not in a hurry. The whole is not the sum of its parts. When you say, my system is slow, what are you actually pointing at? Is it the database, the ORM, the way data flows through the pipeline? Often, the real culprit is the arrangement, not the ingredients. A system is made of 3 things: elements, interconnections, and a purpose. In a web app, the elements are services, databases, caches, queues. The interconnections are how they talk. HTTP calls, events, shared state. The purpose, the thing we rarely write down, is what the system is supposed to achieve for a user. Allow customers to check out in under 2 seconds. For example, not keep all microservices up. Most debugging and most architecture discussions focus only on elements. We replace the slow database with a faster one. We add more replicas. These actions treat the system like a bag of bricks, heavier here, lighter there, but a bag of bricks doesn't have interconnections. When you shift to systems thinking, you start to see that the performance problem may live in the wires between the bricks, a loop that runs 10 times instead of once, triggered by a delay in a downstream service. That's an interconnection problem. No amount of database tuning will fix it. A simple way to practice. Before you open a profiler, take out a piece of paper. Draw a circle for each major element that's involved in the slow request. Draw arrows between them. Label the arrows with what flows: data, control, money, time. Don't try to make it perfect. Just make the hidden visible. You'll immediately see things you missed. A service you forgot, depended on a third-party API. A cron job that kicks in at the worst possible moment. That's the first shift. From seeing parts to seeing relationships. Feedback loops. The real source of behavior. The most useful thing I ever learned about systems is this: behavior comes from feedback loops, not from individual parts. A feedback loop is a circular chain of cause and effect that either reinforces itself or balances out. There are 2 kinds. A reinforcing loop makes more of the same. Success breeds confidence. Confidence leads to trying harder things. Trying leads to more success. In systems, that same structure can be a runaway train. Imagine a cache that stores results. More cache hits mean fewer queries to the database. That frees up resources, which makes the application faster, which attracts more users, which generates more cache hits. That loop can grow smoothly until it crosses a threshold and the cache memory exhausts the machine. A reinforcing loop that once helped you now silently pushes the system into a cliff. A balancing loop, on the other hand, resists change. You deploy a new feature and suddenly the error rate spikes. The load balancer notices. shifts traffic away from the new instances, and the error rate stabilizes. That's a balancing loop. It's your friend, until it hides a problem you're trying to fix. I once spent 3 days wondering why a bug fix didn't take, only to realize a retry mechanism was compensating for the original error so well that the symptom disappeared. But the cost was a 20% increase in latency that nobody noticed until a slower customer complained. Here's the insight. Every persistent problem in a code base has a feedback structure keeping it in place. When you only treat the symptom, the visible bug, the structure remains and the symptom will return, maybe dressed differently. Instead, ask, what is the loop that produces this behavior? Draw the loop. Show it to a colleague. The conversation changes. You stop saying the server keeps crashing and start saying we have a reinforcing loop where increased load triggers a timeout. The timeout triggers a retry storm. The retry storm increases load, and then it crashes. Now you can break the loop at several points. Reduce retry aggressiveness, add circuit breakers, or increase capacity at the choke point. The difference isn't technical skill. It's seeing the circle instead of just the crash. Delays. The silent destroyers of intuition. There's a special kind of feedback loop that tricks even experienced developers, the one with a delay. When the effect of your action shows up minutes, hours, or days later, your brain naturally disconnects cause from effect. You fix something, nothing happens, so you fix something else. Later, both fixes interact in ways you didn't predict. The classic example is a CI pipeline. Someone adds a linter rule. The build time increases by 30 seconds. Nobody notices for a week. Then the team adds another check, another 30 seconds. After a month, the build takes 9 minutes. Everyone complains, but they blame the hardware. The delay masked the accumulation. In system terms, your team was inside a balancing loop with a long delay. The improved code quality goal kept adding constraints, while the keep build fast feedback arrived so late that it never corrected the first few changes. Suddenly the snapback is harsh. Someone proposes removing all linting, which is an overreaction that creates its own loop. When you see a problem that seems to have no single cause, look for a delay. I now habitually chart the sequence of events over time, not just at one point. Even a rough timeline on a whiteboard can expose that the memory leak started 7 hours after the last deploy, right when a scheduled data export kicked in. A delay of 7 hours made the team swear the deploy was unrelated. Delays also teach us patience. If you're optimizing a system, don't keep twisting knobs every 5 minutes. Make one change, wait for the system to settle, then observe. That's the opposite of move fast and break things. It's more like sailing. Adjust the sail a little, feel the boat respond, then decide the next move. Leverage points, where small changes make big waves. Not all parts of a system are equal. Some points, if you change them even slightly, ripple through the whole thing. These are called leverage points. Donella Meadows, who wrote the clearest book on systems thinking, said, "Leverage points are often counterintuitive. We push on the obvious part because it's visible, but the real leverage is elsewhere. For example, the performance of a web app. The obvious push is, buy faster CPUs, but often, a tiny tweak in the database index, a one-line change, gives a 10x improvement. That's a leverage point. It's not expensive, it was just not obvious. Leverage isn't just about performance, it's about any behavior you want to shift. If your team keeps building the wrong thing, adding more process, more stand-ups, more planning meetings, is the obvious lever. The real leverage might be clarifying the decision-making authority, who actually says yes to a feature, or reducing the number of handoffs. I once saw a team cut rework by 60% by giving designers direct access to component storybook instead of passing static mock-ups. That's a structure change, not a people change. Here's how I look for leverage points now. I ask, if I could change one interconnection, what would I change? Because leverage usually lives in the arrows of your diagram, not the boxes. Changing the protocol between two services, say, from polling to webhooks, often has bigger impact than optimizing either service. In a code base, it might be the contract between modules. Enforce a clear interface, and you suddenly contain chaos on both sides. Beware. Leverage points can also work against you. If you push the wrong one hard, you might break the system's self-correction. So apply changes gently and watch the whole system's response over time. Back to the idea of delays. The trap of local optimization. This is the most common pattern I see in code bases, and I fall into it myself constantly. A developer makes one function blazingly fast. It shaves 200 milliseconds off a request. The team celebrates. But that function feeds into a queue that feeds into a batch processor that runs once a minute anyway. The 200 millisecond saving makes zero difference to the user. Meanwhile, the developer spent 2 days on the optimization. 2 days that could have been spent on the queue, which would have saved 40 seconds. That's local optimization. We do it because the function is close to us. It's our code, our responsibility. The system as a whole is someone else's problem. But in a complex system, local optimization often degrades the global outcome. It's like making the bow of a ship point perfectly east when the current is dragging the whole vessel west. The bow is optimized, the ship is still lost. The cure is simple but uncomfortable. Always define the system's goal before you optimize a part. If the goal is user can complete checkout in under 3 seconds, then every optimization must be measured against that. If the goal is developer can understand this module in under 10 minutes, then readability matters more than performance. Write that goal on a sticky note. Keep it visible. When you catch yourself micro-optimizing, pause and ask, does this serve the goal, or am I just polishing a piece I happen to like? One practical ritual. During code review, instead of jumping straight into syntax, ask, what system behavior does this change? It shifts the conversation from the local to the global, and it's surprisingly calming. Because now you're not arguing about taste, you're aligning on purpose. We covered 5 perspectives, seeing systems, not just parts, tracing feedback loops that generate behavior, respecting delays that hide cause and effect, finding leverage points that give you outsized influence, and avoiding the seduction of local optimization. If there's only one thing you take away, let it be this question, the one I now tape to the top of my monitor. What is this part's purpose in the whole system? Ask it when you design a function. Ask it when you get a bug report. Ask it when you decide what to work on this morning. The hard part isn't the code, it's the clarity. And clarity comes when you stop treating software like a collection of standalone machines and start treating it like a living, shifting sea. The boat doesn't move by pulling at the planks. It moves by understanding the wind and the current and making small, calm adjustments. If this way of seeing the world felt useful to you, consider subscribing. There's no algorithm chasing here, just quiet, slow conversations about the craft. I release a new video every 2 weeks. No rush, no pressure. Thanks for watching.